In this video, we consider maximum likelihood estimation of the AR1 model. We start out by considering the case where we have a set of observations that are drawn from an IID process, and we seek to estimate the model parameters by maximum likelihood. So we consider the case where we have a set of observations xt from t equal 1 to time capital T. The observations are independent over time and they are drawn from the same distribution, and we assume that xt has density f of x, and we index the density by a parameter theta, and our objective is to estimate theta. Now, recall that we can write down the likelihood function of the observations. This is simply just the joint density of the observations. And now, due to the fact that the observations are independent, we have that the joint density of the observations is the same as the product of the marginal densities of the observations. Hence, we obtain the log likelihood function, which is just the sum of the log of the likelihood contributions. And we can estimate theta by simply maximizing the log likelihood function. Now we consider the autoregressive model of order 1. We have that the model is given by yt, that is equal to phi times yt minus 1 plus epsilon t for observations t equal 1 up to time capital T. We assume that epsilon t is independent and identically distributed over time with a normal distribution with mean 0 and variance sigma squared. We condition on y0, so we can consider y0 as fixed or known. Our objective is to estimate the model parameters phi and sigma squared. These are contained in the vector theta. We know for this process that for phi being different from 0, that the process is dependent over time, meaning that we cannot rely on taking the sum of the marginal densities in order to obtain the likelihood function of this model. Instead, we will rely on another trick, namely the definition of the conditional density. Recall that the conditional density of, say, y given x is the same as the joint density of x and y divided by the marginal density of x. We will use this result in order to derive the likelihood function for the autoregressive process. Now, for the sample from observation 0 up to observation t, we can write down the joint density. Now we can use the trick stating that the joint density of y0 up to yt is the same as the conditional density of yt given observation yt minus 1 down to observation y0 times the joint density of observation 0 up to observation t minus 1. Next, we can consider factorizing the last factor in the product, such that we have the conditional density of yt and then times the conditional density of observation yt minus 1 given yt minus 2 down to observation y0, then times the joint density of observation y0 up to observation yt minus 2. then we can proceed with this factorization such that we in the end will end up with the product from t equal 1 to capital T of density, conditional density of yt given yt minus 1 down to observation y0 times the density of y0. Next we want to find an explicit expression for these densities, and in order to do that we will use some properties of the model. Note that due to the structure of the model, yt does only depend on yt minus 1. It means that the conditional distribution of yt given the previous values is the same as the conditional distribution of yt given yt minus 1. This implies that the conditional density of yt given the past is the same as the conditional density of yt given yt minus 1. Moreover, we know due to the fact that epsilon t is normally distributed, we have that yt conditional on yt minus 1 is normally distributed with some conditional mean yt given yt minus 1 and a conditional variance of yt given yt minus 1. In particular, the conditional mean of yt given yt minus 1 is phi times yt minus 1, and the conditional variance of yt given yt minus 1 is equal to sigma squared. Hence the conditional density of yt given yt minus 1 is simply based on the Gaussian density. Particularly we have 1 over the square root of 2 times pi times the conditional variance of yt given yt minus 1 times the exponential function of minus yt minus the conditional mean of yt squared divided by 2 times the conditional variance of yt, which we know is equal to 1 over the square root of 2 pi times sigma squared times the exponential function of yt minus phi times yt minus 1 squared minus then over 2 times sigma squared. We can then write down the conditional likelihood that is simply given by L of theta, which is the conditional density of y1 up to yt conditional on y0, and that is simply given by the product of the conditional densities of yt given yt minus 1. Lastly, we can consider the maximum likelihood estimator of theta, called the log likelihood, is simply just the sum of the log likelihood contributions in particular. It can be shown that the maximum likelihood estimator for phi is simply the average of yt minus 1 times yt divided by the average of yt minus 1 squared. This is exactly the OLS estimator for phi. Likewise, the maximum likelihood estimator for sigma squared is simply the average of the squared residuals, where the residual epsilon t hat is given by yt minus phi hat times yt minus 1. Thank you for watching.